All right, so the next topic slated for the book is logarithmic functions. And before we start talking about logarithmic functions, we really should be talking about inverse functions, because that's what a logarithmic function is all about. It's the inverse of an exponential function. So for instance, if we have f of x is equal to 2 to the x, and the cool thing about this type of function is if you plug in a number, say 3, into x and you evaluate f of 3, you're going to get 2 to the third, which is equal to 8. And the neat feature is 3 is the only number you can plug in to get to 8. So 3 is the only x value that gives you a y value of 8. No other x values give you a y value of 8 when you plug it into this function. Therefore, this function is known as one-to-one. For every x, there is a unique y. Okay, so another way of looking at this is if we look at f as a function of an individual value in the domain 3, and it brings you to an individual range value of 8. So we can read this as f takes 3 and brings you to 8. Shorthand notation for this is literally the coordinate. 3 brings you to 8. So if we're talking about an inverse, it's denoted this way, f inverse, should take 8 and bring you back to 3. So the best way to describe this is to change it into English. So we can change the f of x equals 2 to the x as a kind of a question. So what number will I get when I take 2 and raise it to a power? Okay, so what number will I get when I take 2 and raise it to a power? So if I raise it to the third power, like down here, then I'm going to get this number. So the answer to the question is the 8. So the answer to the question actually is the range of the function. So if we're talking about the range of a function, then this part, what number will I get? That's the range. And the power, raised to the power down here, is the domain. It's the number I'm plugging in. So if I'm going to invert it, then what will happen is the language is going to switch. So if I do the inverse down here, something that's f inverse that takes 8 and brings you back to 3, should read, what power do I need on 2 to get 8? Or what power do I need on 2 to get a specific number? Eight's just a nice one to work with. So if we go in this direction, then this part, what power do I need on 2, that becomes our range. So the answer of the inverse function of an exponential function is going to be a power, and the specific number that we're trying to find this power of 2 to become is the domain. So there's no fancy notation that we have available at this point, kind of like exponential functions. Those are easy because they're just powers. So we're going to need to come up with a new notation, and we're going to use, obviously, this word up here, logarithmic. Okay, so if we're talking about a logarithmic, then the question was, what power do I raise 2 to get to a specific number? We're going to shorten that down to be log, and put a little 2 down here, and then the number would go there. So this is red, log base 2 of x. Log base 2 of x. And it literally is the same thing as the question I asked before. What power do you have to raise 2 to get to the specific answer of x? So it basically is just the question as a function. So we can write this as, off the page, f of x is equal to, and it's actually the inverse of the original f of x on the other page, log base 2 of x. All right. So if we have a function, for example, that was g of x is equal to log base 5 of x, and I want to evaluate 25, that would be log base 5 of 25, then the question becomes, what power on 5 gives you 25? And the answer to that, of course, is 2. 5 squared is 25. So g of 25 is going to equal 2. So the question actually helps you answer what a logarithm is. All right, so the second thing is we know that a logarithm is an inverse function of an exponential. So if I write f of x is equal to 5 to the x, then f inverse of x, its inverse function, is going to be log base 5 of x. Now we have to talk about another property of inverse functions. So let's work with a nice simple function. Let's say f of x is equal to x cubed. Now, one process of finding an inverse is to replace the f of x with y, and then switch the x and y. So now we're not talking about the original function anymore. So we have x is equal to y cubed, and solve for y. So to get rid of a cube, you cube root both sides, and you get this. Now, cube roots don't need the plus or minus. Otherwise, this would not be a one-to-one. Technically, it wouldn't be a function when you solved it down to this point. But this would be considered its inverse function. So we're going to write it as f inverse of x must be equal to the cube root of x. So one of the properties of inverse functions is that if you compose them with each other, something fancy happens. So let's compose them with each other. Let's do f inverse of x first. So this would be take f, which is x cubed, something cubed, and plug in f inverse, which is the cube root of x. So what happens when a cube root hits a cube? Well, your answer just becomes x. Let's go the other direction. F inverse of f of x. Well, that's going to equal, the main function now is f inverse, the outside function, which happens to be the cube root of x. Ooh, let me back up here. It doesn't go there. It goes here, the cube root of x. And what goes inside is f of x, which is over here, x cubed. So you'd have x cubed inside. And when you cube root an x cubed, your answer is x. So the main property of inverse functions is if you compose them with each other, your answer is always going to be the original domain that you started with. So if that's a property of inverse functions, then if I do log base 5 of 5 to the x, the answer better be just plain old x. Because 5 to the x is a function. Log base 5 is its inverse function. They can't, I don't like saying that word, cancel. They undo one another. Another word I like using is poof. They go poof and you're left with x. So similarly, if you have 5 raised to this weird power log base 5 of x, again, they are inverse functions. And if the original function is log base 5 of x, the other one is 5 to the x is its inverse, and they go poof, and you're left with x. So the way I kind of think about it is here, the 5s are close enough and they're touching each other and there's really nothing else going on there. Then all of this is going to go away and you're just going to be left with the x up top. And here, similarly, the two functions are touching one another. Therefore, they kind of go away and you're just left with x in both cases. So it's different ways you can kind of look at it. All right, let's do a couple examples of evaluating logarithms. So if you have log base 7 of 49, I usually teach it two different ways. One with the question of what power do you raise 7 to get 49? The other way I teach it is I let this thing equal x, and I rewrite it as its inverse. In other words, in exponential form. So if I was going to write it in exponential form, this down here is the base. This x that I set it equal to, the answer of this thing is x, is going to be the power, because it's what power do you raise 7 to get to 49? So the answer is the power. And then, of course, the 49 is the answer of an exponential. So if I reorder this, it would be base of 7 raised to what power is equal to 49. And this goes back to the exponential section of how do you solve one of these equations. Well, you write the both sides in terms of a number, a single base, and 7 seems to be the easiest. So I'm going to write this side as 7x, and 49 is 7 squared. And because the bases are exactly the same, we can just say, or deduce, that x must equal 2. So, therefore, I like using my little 3 dots, that represents therefore, log base 7 of 49 has to equal 2. So it depends on, your style of doing these problems, if you set it equal to x and change it to an exponential, or if you just ask the question. Some of them get kind of confusing, so asking the question sometimes doesn't end up with a good answer. Change colors. What if I have something a little weird, like log base 1/2? Bases can be the exact same bases as the exponential bases, so any number between 0 and 1, and any bigger than 1, just not 1 and definitely not 0. So log of 1/2 is equal to 16. Log base of 1/2 is equal to 16. So asking the question, what power do you raise 1/2 to get to 16, sometimes just doesn't jog people's brains. So the best thing to do is to add on the idea of letting it equal x, where x is the power and 1/2 is the base. So this becomes 1/2 raised to the x power. Now notice I'm putting the 1/2 in parentheses. You're not just raising the 1 to the x, you're raising the entire thing to the x, is equal to the answer, and the answer happens to be 16. Ooh, one little small thing to notice here when you're looking at this, notice that the x is going on the opposite side of the equation, and the same thing for the 16. They're flipping positions in our equation, and that's really important because remember, when you're going to an inverse function, you have to flip the domain and range. So x over here in this case is the range, and when you change it into its inverse function, it becomes the domain. And the same thing for the 16. The 16 up here is a domain because you're plugging it in, and over here it's an answer, so that's a range. Okay, let's get rid of all those circles. So let's solve this equation from the previous section. Number 1, working with fractions is a pain, so I'm going to bring the 2 up. Go back to green. So if I bring the 2 up, you have to remember that if you bring things through a fraction bar, it changes the sign of the exponent. So we get 2 to the negative 1 raised to the x is equal to, and now I want to change 16 into this common base of 2. Well, 16 is 2 to the 4th. So on this side, we have 2 to the negative x, power to a power you multiply, is equal to 2 to the 4th. And again, once we get down to the bases are exactly the same, we can deduce that negative x must equal 4. It's a property of one-to-one functions too, which is kind of nice. And therefore x is equal to negative 4. So that means, if we go back to the beginning, that log base 1/2 of 16 must equal negative 4. So that's how I would solve most of my logarithms, because it's easier, I think, to solve them in exponential form than it is to try to think about what power it is. Right. Here's my last example for just evaluating simplistic logarithms. Again, we have a weird fraction going on. So we have log base 3 of 1/81. So what power do you have to raise 3 to get 1/81st? So again, I'm just going to set it equal to x and rewrite it as an exponential function. So 3 raised to the x is equal to 1/81. So the common base that we're going to be looking for is 3. So we're going to change him into 3 to the x. I don't like the 81 in the denominator, so I'm going to bring it to the top. So it becomes 81 to the negative 1. Because anytime you move from the bottom to the top, the exponent has to change sign. So this is 3 to the x is equal to, now 81 is 3 raised to the 4th power. It's 9 times 9, and 9 is 3 squared each. And that'll be raised to the negative 1. So you get 3 to the x is equal to 3 to the negative 4. So x, by chance, then has to equal negative 4. So we can go back to the original notation and write it as log base 3 of 1/81 must be equal to negative 4. So one of the properties of logarithms that I'm using, and exponentials by the way, is the property to interchange them. So we can say that this is a property. Log base b of x is equal to y is the same thing, or is interchangeable with b, the base, raised to the power now is y, is equal to the answer, which is x. So this notation, this double arrow here, is basically just saying interchangeable. You can replace one with the other or vice versa. Get rid of that. So if you have b to the y is equal to x, you can replace it with log base b of x equal to y. So just a couple silly little examples. These usually aren't too hard. I'm going to make them as messy as possible, of course. Log base b of 2x minus 1 is equal to 3y plus 7. Why not? As ugly as possible. But it's really not too hard. So the base is b. So we would write that first if we're going to rewrite this as an exponential. The power is the other side. So when we talk about this, we're going to say base b, the power is going to be the other side of the equation, so 3y plus 7. And it's going to equal the answer, which is what log is looking at. So this would be 2x minus 1. And that's it. Pretty simple. Some high schools teach it calling it loggy froggy, but I hate that because if it's in the opposite order, loggy froggy doesn't work out really well. So let's try another example. Let's say 47 is equal to log base the square root of 2, as ugly as I can get, 3x plus 1. All right, now I've reversed the order, but that shouldn't really hurt anything. So we're going to start the same way. The base here, weirdly enough, is square root of 2. So when I say, what is the base of my exponential going to be? It's going to be the square root of 2. Now the square root of 2 is on this side of the equation, so the power has to be on the other side of the equation. So we're going to say the power is 47. And it's going to equal 3x plus 1. And the cool thing about writing it this way is now we can actually solve for x. We got x in a place where you can solve it, where before x was locked inside of a logarithm and you couldn't go anywhere with it. So that's where this property comes in really handy. If you ever get stuck with a logarithm, you can always change it to an exponential and vice versa. Some basic principles, part of things I've talked before and some things that go back to like laws of exponents, would be the inverse principle. If you have something like log base 7, oh, that's cool, of 7 raised to the 19th power, then this becomes actually an easy question to answer, because there's two ways of looking at it. You can say, what power do you have to raise 7 to get 7 to the 19th power? Well, the answer is staring you in the face right now. It's this 19 up here. So another way of looking at this is they're inverse functions. This is log base 7 and then base 7 exponential, and they're touching each other here. So basically these two are going to go poof, and you're just left with 19. So one of the properties is if you have log base b of b raised to some power, let's call it n, then the answer is automatically just going to be n. The b's will basically go poof, and you're left with the n up above. All right, law number 2. And this is a good one. 2. And if we have log base b of b, so what power do you raise b to get itself? Well, the only exponent that you can raise something to and not change the number is 1. B raised to the first power is b. The third one is a little bit more confusing for most people. What power do you raise b to get 1? And if you remember back with the laws of exponents, that we had any number, let's call it a, oops, let's call it a, if it's raised to the 0 power is equal to 1. That was a law of exponents that we covered earlier. So here we're saying, what power do I raise b to get to 1? Well, the power has to be, well, 0. So 0. So these are 3 nice ones to know offhand, because it allows you to simplify things. You can get rid of this ugly notation up here and replace it with a single n. You can get rid of this ugly notation and simplify it down to 1. And you can get rid of this notation and simplify it down to 0. All right, so let's start talking about graphs of inverse functions. So graphs of inverse functions, let's kind of backtrack and talk about just graphs of any inverse functions. So let me draw a grid in here as best I can. The grid's already here, but drawing a straight line with this is not perfect. So if we go back and talk about what's the graph of a function and then its inverse, we can look at a function that we know pretty well. Let's say the cube root of x, or pretty much anything. So let's have the cube root of, or the cube of x cubed. So it comes down like this and then continues on its merry way. So this is kind of what the cube function looks like. So this would be x cubed. So to find its inverse, the best thing to do is to start locating points on it. Now, don't count by grid. It's not a perfect graph. So I'm just going to generate some points on here and kind of label them. 0, 0 is an easy one. If you raise 1 to the 3rd power, you would get something like 1, 1. If you raise 2 to the 3rd power, you would end up with 2, 8. And of course this is 0, 0. And if you plugged in -1, you would get a coordinate over here of -1, -1. -1 to the 3rd power is -1. And if you plugged in -2, you would get a coordinate down here of -2, -8. So when you're talking about an inverse function, literally all it does is take the two coordinates, or the coordinate, and flip them. So the x becomes y, and the y becomes x. So we're going to just take each one of the points and rewrite them as yx. And that will be our inverse function. So let me try drawing some more straight lines to graph my inverse function. Hey, that's not too bad. Let's do blue. So I'm going to reverse the order. So 2, 8 up here is now going to become 8, 2. So we're going to go out 8 and then up 2. So this would be 8, 2. The next point would be 1, 1. And if you flip 1, 1, you get, well, 1, 1. That's not much difference. 0, 0, same thing. It's just going to go through the origin. -1, -1 is going to be someplace down here. And then this one here, -8, -2. So it would be like -8 to the left, down 2. And you'd have -8, -2. So the graph of the inverse function would look something like this. And that literally is the graph of the cube root of x. So that's how you would graph an inverse function. You would just take the two coordinates and flip them. So let's do that with an exponential graph and see what it looks like. So let's see, straight line. Not too bad. Not too bad. Okay. So an exponential graph looks like this. It goes through this point up here of 0, 1. It hugs, I probably should choose a brighter color. It hugs the negative x-axis as it goes to the left, goes through this point 0, 1, and then grows exponentially. So if this was f of x equals 2 to the x, that would be a nice picture of what it looks like. So if we're going to invert this, we're going to need to take the points, or some points on this graph, and flip them. So I'm just going to make up a few points. So let's say this one here is if you plug in x is equal to 1, you're going to get 2. If you plug in x is 2, you're going to get 4. If you plug in 0, of course, you're going to get 1. If you plug in -1, you're going to get a half. And we've talked about this a lot earlier, too. If you plug in -2, you're going to get a fourth. All right, so those are points on the exponential graph. So logarithm being its inverse, log base 2 specifically, then its graph is going to reverse each one of these coordinates. So let's reverse all the coordinates first. So 2, 4 becomes 4, 2. 1, 2 becomes 2, 1. 0, 1 becomes 1, 0. Ooh, I got the points too close to each other. Let's put it like right about here. All right, let me label these. So this one is 4, 2. This one is 2, 1. This one is 1, 0. And then when it gets to the tricky ones, so -1, 1/2 becomes 1/2, -1. So it's like here. So that would be your 1/2, -1. And then we have -2, 1/4, which is going to become 1/4, -2. So it's got to get even closer and go a little bit further down. So here, when you're talking about an exponential function, it has a horizontal asymptote of the negative x-axis. So that means when we draw it for its inverse, it's going to switch and become the negative y-axis. So the negative x-axis horizontal asymptote transforms into a vertical asymptote along the negative y-axis. So our graph is going to hug the negative y-axis, go through 1, 0, and then slowly grow. Where an exponential function rapidly grows, logarithmic functions are going to slowly grow. So this would be the base function of what a logarithm graph looks like. So as long as the base is bigger than 1, and you always want to work with logarithms with a base bigger than 1 when you're graphing, because otherwise it gets very confusing. The base graph is hug the negative y-axis, go through this point. That point will always be 1 to the right of the intersection of the origin, so this would be 1, 0 in this case. So the base graph would look something like this. Now there's no asymptote on the top part up here, but there is an asymptote on the bottom part here. So it has to approach the y-axis, but it never ever touches it. It just goes straight down it. So this would be the graph of f of x equals log base b of x as long as b is bigger than 1. So once we have a base graph, then we can start talking about transformations on this graph, domain and range of the graph, and all that fun stuff. So now we have a base graph of a log with a base larger than 1. So this up here would be log base b of x. Hugs the negative y-axis, hits 1, 0, and takes off rather slowly. Down here, we're going to graph a transformation. So we have to remember what each one of these pieces do. So inside the parentheses or inside the function, this x, the number next to the x, is going to go opposite direction. So this is going to go 3 left. Because to make that equal to 0, you would have to put in x equals negative 3. Here, it's outside the function, so it's going to affect the y value, so this is going to go 2 down. And remember, in the exponentials descriptions, we talked about imaginary axes. So we're going to go 3 left, so that would be over here. We'll have a vertical imaginary axis, and it becomes an asymptote on one side of it. And then the 2 down would be horizontal axis, representing the x-axis. Then, when we start plotting these points, we have to remember that the axis used to be here on this picture up here. Oops. And when we looked at that, it was always 1 point to the right that we would plot that special point, and then also that would become the vertical asymptote. So when we're at this crosshairs here in this location, then what we need to do is, since it's all positive except for that, down 2, the graph itself is going to move 1 to the right. So we're going to plot this point. It's going to have the same behavior as this graph. It's going to start along the negative y-axis and then shoot off rather slowly. This one, though, is going to come up this vertical representation of an axis, hit this point, and grow really slowly. So this becomes the vertical asymptote, and this point has a coordinate of -2, -2. And that would be a good sketch of log base 2 of x plus 3 minus 2. All right, so let's look at this graph here. We want to graph g of x equals 3 minus log base 2 of x minus 2. So we'll just go through it piece by piece, figuring out what everything does. So let's start with the inside. I always like starting with the inside. So here we have x minus 2, so to make it equal to 0, it would be positive 2, so this would be going 2 to the right. The 3 out front here, a lot of people get confused with it because it's usually in the back end. It's still a positive 3, and it's still outside of the logarithm, so this is going to go up 3. Now, the only thing that gets really weird about this, and I generally don't put a negative in front of x for logs, it just gets too weird, is this negative in front of the log. It's changing the y values from positive to negative. So this thing is going to flip over horizontal, wherever that horizontal imaginary axis ends up, this graph is just going to flip over that line. So let's get our lines in there for up 3 and right 2. Let's do right 2 first. So this would be right 2, x equals 2. And up 3 would be up here. Oops, don't want that. So it's kind of high on this graph. So, and the other thing is, being negative in front of it, the point that is 1 to the right of the intersection of these axes is now going to be pretty much in the same location, because if I flip over the horizontal line, this point's not going to go anywhere. So this will be a guaranteed point on this graph. Now, you have to remember that a regular logarithm graph, and I'm just going to draw a quick sketch here, looks something like this. It crawls from the bottom and then grows slowly in that direction. So if I flip it over the, in this case, the x-axis, the graph is going to change direction. It's going to come down the positive y values, hit that point 1, 0, and then grow negatively slowly. So I know my graph is going to be coming down from up above along this vertical asymptote, and then hitting this point and then growing slowly. So you get a graph that looks like this. Maybe I should move it. Here's a better view of that graph of f of x equals 3 minus log base 2 of x minus 2. And this is what it would really look like. Notice it's hugging really closely up here, the positive side of the y asymptote, and then growing slowly as we cross that side. The reason that you want your base to be larger than 1 is the question of how do you graph this? So the problem here is having this 1/2 in the base position, because that makes things a little confusing. So here's a workaround to having a base less than 1. We're going to first set this equal to y, and then we're going to change it into an exponential form. So the base is 1/2, the power is y, and it's equal to x minus 3. And then we're going to kind of solve for y from this point, or get it back into terms of y. But I want to get rid of the 1/2 first. So this becomes 2 to the negative 1 raised to the y power is equal to x minus 3. And then power to a power you multiply, so you get 2 to the negative y is equal to x minus 3. So at this point, we've gotten the 1/2 power down to just 2. So I'm going to change it back in to logarithmic form. So if I change it back into logarithmic form, we're going to get log base 2 of x minus 3, remember it's the opposite side of the equation, is equal to negative y, which is the same thing as graphing y equals negative log base 2 of x minus 3. So having the 1/2 up here at the top is exactly the same as a negative in front of the log when you change the base into its reciprocal. So the graph of this, just real quick, the negative 3, the x minus 3 here would move it right 3. So you'd have this vertical asymptote over here at x equal, well, yeah, it is an asymptote, x equals 3. And the negative here is going to flip it over the horizontal. So normally, remember, a logarithm graph usually starts low and grows slowly upwards. So this one's going to flip, so it's going to come down, hit this point here, which just happens to be 4, 0. It's 1 to the right of 3. It's going to crawl down here, hit this point, and grow slowly. Calculators do take care of logarithms. One of them is called a common logarithm, and a common logarithm is a log whose base is 10. Now on a calculator, all you're going to see is log. So when you see log by itself, it's understood to have a base of 10. So log of x is the same thing as log base 10 of x. There's also something called the natural logarithm. Or the natural log. And the natural logarithm is a log whose base is this special number e of x, and we're going to rewrite it as just ln of x. So if you see ln, then you know the base of the logarithm is e. So for example, if you're trying to evaluate the log of 100, then this is the same thing as log base 10 of 100. So what power do you raise 10 to get to 100? Well, the answer is 2. 10 squared is 100. And also, if you're dealing with ln, if you have ln, and really the only simple ones is it has to have an e in it, of e to the 7th, then this becomes log base e of e to the 7th. And we can use the inverse properties of logarithms, where these two are touching each other and they go poof, and all you're left with is 7. So the ln of e to the 7 is equal to 7 because of the inverse properties of logarithms and exponential functions. So that's just the common log and the natural log. So again, it's really important, if you do not see a base under a log, it's understood to be 10. And if you see this ln thing, you have to remember the base is e. Probably one of the more confusing things for people to deal with is cube roots, square roots, and how to deal with them as powers. So ln and e are not touching here, kind of like here they're touching. So they kind of go poof and you're left with 7. Here they're not touching. We've got this cube root in the way and we have the square on the e. So we need to get the ln and the e touching before anything else. So a cube root of any number is the same thing as that number raised to the 1/3 power. Square roots of a number are that number raised to the 1/2 power. I think I talked about this with laws of exponents. So it comes in handy here. So this becomes ln of e raised to the 1/3 power. Back up a little bit. It was squared first. And then that would be raised to the 1/3 power. So then back to the laws of exponents. Power to a power, you're going to multiply these guys. So you're going to get ln of e to the 2/3. So now that ln and e are touching each other, they're going to go poof, and your final answer is 2/3. All right, so let's start solving equations again. So a log equation basically can look like this, something like log base 25 of some number x is equal to -3/2. Now this is the case where, you're trying to get x by itself, and it's locked inside of this logarithm. So you want to basically get the log out of there, and one of the only ways to do that is to change it to an exponential function, or an exponential notation. So the base of the exponential would be 25. Change colors. And the power on the 25 would be on the opposite side of the equation. So this would be -3/2 as the power is equal to the other side of the equation again. So remember, this is inverse function. So it's one side to the other. You're flipping them. All right. So how do I take 25 to the -3/2? In previous videos, I've told you that the square root of a number is the same thing as the number raised to the 1/2 power. So one way of looking at 25 to the negative 3 halves is to look at it as 25 to the 1/2 power raised to the negative 3. Because power to a power you multiply, and I know negative 3 times 1/2 is the same thing as negative 3 halves. All right, now we have that 25 to the 1/2. That's the same thing as the square root of 25, and that's going to be raised to the negative 3rd power. And then the square root of 25, of course, is 5. And then by laws of exponents, a negative exponent means it's on the wrong side of a fraction. So this becomes 1 over 5 to the 3rd. And 5 to the 3rd is 125. So we get down to a solution that x is equal to 1 over 125. All right, let's solve this equation. Now, this one might require a calculator, so let's be prepared. The base of this problem is, it's a common log, so you need a base of 10. So the base is 10, the exponent is negative 1, and it's equal to 4x. And we're trying to solve for x here, so 10 to the negative 1 is the same thing as 1/10. So we have 1/10 equals 4x. All right, now to solve for x, we need to get rid of the 4, so we're going to divide by 4 on this side. And then it gets a little tricky over here. Do I want to divide 1/10 by 4? So another way of writing divide by 4 is to multiply by 1/4. Since it was in the bottom over here, we can just put it in the bottom over here. So 1/10 times 1/4 is 1/40th. So we get x equals 1/40th. Oh, good. We didn't need a calculator on that one. Let's try one where you do need one. So, for example, what if I have ln of x squared is equal to 7? This will be definitely a calculator one. All right, so start off the same. The ln has a understood base of e, so this becomes e to the 7th is equal to x squared. Now we're trying to solve for x. X is the variable, e is a constant, kind of like pi. So it's a number raised to the 7th power. So to get rid of the square, we're going to square root both sides. So this becomes x is equal to the square root of e to the 7th. And if you remember back from like Math 171, if you square root both sides of an equation, you have to add in a plus or a minus. Now we get into another discussion. Can x equal a negative? Well, in this case, it can because it's being squared. If that square was not there, then x would only be positive the square root of e to the 7th, because you cannot take the log of a negative number. It's not part of its domain. All right, so I can keep for the square root of e to the 7th. So it's about 2.718. Oh, that's not it. 7. There we go. 33.12. This would be approximately 33.12.